Good day, grade 12 learners. Welcome to today's geography lesson. My name is PC Pejani and I'll be presenting the lesson with PC Zondi. This lesson is proudly brought to you by the Gauteng Department of Education in collaboration with Saibono Discovery Center. Today's subtopic will be drainage systems in South Africa plus a map work. Our lesson objectives is just like we have always said. You must know the definitions, identification, and application of your content. We will be looking at the drainage basin, catchment area, river systems, tributary, confluence, watershed, interflow, source of the river mouth, surface, runoff, infiltration, groundwater, and water table. You must be able to define the impacts of and factors that influence drainage density. Why do we have high density in some places and low density in others? And you have to be able to define and explain precipitation, evaporation, soil moisture, vegetation, slope, porosity, and permeability, which are the factors that will be affecting your density. So these are the factors. You must be able to explain how does precipitation influence density, how does evaporation influence density, how does soil moisture influence density, how does vegetation or absence of vegetation influence density, how does the slope or the gradient influence density, then porosity and permeability, which are very related to each other. We'll see about how does porosity relate to permeability or other way around. And then in our map work, we are going to be looking at cross sections, intervisibility. You know, when you're drawing cross section, you're taking contour lines and you're making a feature that looks like those contour lines or that is represented. Intervisibility simply refers to can you see one point from another. That's what intervisibility is. And we'll be calculating vertical exaggeration. And then why do we calculate vertical exaggeration? Study tips for the week is like what we always tell you to do your study over this weekend. Use previous question papers, listen to the videos, identify subtopics that you don't understand and go to class for more assistance. You must draw mind maps. Mind maps are very helpful. You draw a mind map, then you put all aspects that could be relating, and you know your geography questions: what, where, why, and how. So those are the geography questions that you need. So when you do your mind map, it will help you very much. Now let's look at drainage basins. These are the concepts that you need to master. Drainage basin, what is a drainage basin? Catchment area, river system, tributary or tributary, however you pronounce it, confluence, watershed, interflow, and the source. Now let's look at our content today. You must be able to define. It's very important. Your questions will ask you to define, and when you define, you just give back the content that was taught to you. There's no application. You just give the content that was taught to you. Identification, you must be able to identify features from the map, features from the diagrams. You must be able to identify them. And application, how does it affect, what does it affect the environment with? You must be able to give those application questions, and that must be done for all of these concepts that you have. Let's look at the drainage basins now. This is our content. What are we looking at here? This is the drainage basin. So this entire area here is called a drainage basin. So what is a drainage basin? It is the total area drained by the river system. So what do you have here? You have the entire area, and you're looking at this is what we call a river system, because you can see it's many streams here that come together. They make what we call a river system. So drainage basin is an area drained by the river system. Let's look at more of our concepts here. When you're looking at this, you're looking at the mainstream and all its tributaries. So you are looking at what is a river system. It is this mainstream, the bigger river, and all the smaller rivers that are flowing into this bigger river is called a river system. The mainstream plus all its tributaries. Now, what do you see? This one is a mainstream. It's a bigger river. We call it a mainstream. And then what do you call that? The small rivers that flow into the bigger rivers are called tributaries or tributaries. Then you see over here, this is where this river is starting. It's called the source. The source of the river is where the river starts. So the source of the river will be found in the upper course. We'll look at that next week when you're looking at the river profiles. So the source of the river will be where the river starts, where the river gets its water from. So the source of the river is usually found in an area that we call a catchment area, which you look at into the second slide here. A catchment area, which means the area that catches. It says catchment. So when you're catching something, so a catchment area is the area that catches rainwater and feed it to the stream, or that receives rainwater and feed it to the stream. So that is where you are going to find your source, in that part of the river. And then what we have here, we have what we call the river mouth. It's not just a mouth, but it belongs to the river, so it is the river mouth. So a river mouth is where the river enters the sea, which means the river at its lowest point, when it enters the sea, that is what we call the river mouth. Then what we have there another concept here. You have this concept here where these two rivers are meeting, all these points where the rivers are meeting, all these points, it's called confluence. Confluence is a point where two streams meet. It can be a tributary meeting another tributary, or tributary meeting a mainstream. So long as there's a joining of two streams, that point is called a confluence. Now let's continue with our drainage basin concepts. What do we have there? We have a watershed. Now, what do we have here? You see we have a dotted line here. So you can see this is a drainage basin, as we say. So this is called a watershed. So what is a watershed? It is a high-lying area that separates two or more drainage basins. So you can see that we have this over here is an area drained by the river system. It is called a drainage basin. So it is separated from any other place by this, what we call this is the high-lying area that separates this drainage basin. This drainage basin is an area drained by the river system, and we have already defined what a river system is. And then what we have there? We have an interfluve. An interfluve is high-lying area that separates streams within the same drainage basin. So what do we have there? We have watershed. What does the watershed do? It separates drainage basins. And then we have an interfluve. What does the interfluve do? It separates streams, but within the same drainage basin. So don't confuse drainage basin to watershed. Watershed separates drainage basins. Interfluve separates the streams or tributaries, but within the same drainage basin. Okay, what do we have now? We have we continue with our concepts. So what do we have here? We have different concepts. Number one, we have infiltration. So after precipitation, water is going to go into the surface. So when water is absorbed by the surface, or the absorption of water by the surface, that process is called infiltration. The absorption, the process by which water on the ground surface enters the soil, or you can simply say absorption of water by the earth surface. That process is called infiltration. And then once this water infiltrates the surface, where is it going? It's going underneath the earth surface. So once that water is no longer on the surface now, it is called groundwater. So what is groundwater? Groundwater is water that is stored within the earth surface, or the water that is stored beneath the earth surface. So first we have the process of infiltration, which is absorption of water by the surface. Now, when that water is now underneath the surface, what do we call it now? We call it groundwater. So groundwater is the water beneath the earth surface. Then we have now water table. Now you can see here is the water that is within the earth surface. We have the water beneath the earth surface. Now this top surface here, this top surface of groundwater, that is what we call the water table. So water table is going to vary in heights. During rainy seasons, the water table will go higher because of there's going to be more infiltration. But during dry season, your water table will subside, will go lower because there's going to be less infiltration. So this is what we call a water table, which is the top surface of groundwater. Now we have what we call surface runoff. So what is surface runoff? Surface runoff simply refers to the flow of water on the earth surface. Is the flow of water on the earth surface. Now this surface runoff can take place in two ways. It can be what we call sheet flow. It can be what we call sheet flow when the water is flowing all over the surface here. When water is flowing all over the surface here in a sheet form, that is going to be called a sheet flow. But now you see here the water is flowing in the stream. So this one we call it stream flow. We call it stream flow. We call it stream flow, or the streams are also called channels. So we can also call it a channel flow. So that is when water is flowing in stream, but it is still surface runoff. It is still what we call direct runoff. So surface runoff can take place in two ways. When water is flowing in streams, what do you call it? We call stream flow or channel flow. Or water is flowing on the surface, openly on the surface, when it is flooded, or water is flowing on the earth surface before it flows into any stream, we call that a sheet flow. So those are the two ways in which water can flow on the surface. And now we have also what we call a through flow, which is now this water is going to be is flowing underneath the surface, but it's now going to get into the rivers. But it is getting into the rivers from, it is the groundwater that is flowing into the streams. So we call that through flow. Let's continue with our concepts. Okay, I said earlier we have what we call a catchment area. Let's look at what we have here. We have this area that we call catchment area. This area over here is called a catchment area. So what is a catchment area? A catchment area is the area that receives rainwater and it supplies the water to the river system or to the river and its tributary. So when it rains here, water is going to flow. It's going to flow on the surface, and flowing on the surface, then it flows into the streams. And as it flows into the stream, this part of the drainage basin, is what we call the catchment area. So you find your source of the river in a point that we call a catchment area. The source will be where the river gets its water from. So the river gets its water from either an area of high rainfall, or it gets the water from underneath a source. There could be a spring somewhere here. There could be a spring where water is flowing to the surface. That could be the source of that particular river. Or it could be an area of high rainfall. It is also a source of the river. So those points where the river is getting its water from is called the catchment area. So your catchment area, the area that receives rainwater, and what does it do with the water? It feeds the water to the stream. Now, what we have here again we have a continuation of that groundwater, which we said groundwater was water on the surface, and we have all these other surfaces, other processes that are taking place here, your evaporation and wind direction taking water, the clouds straight to the source where it's going to bring our rainfall. Now this is our continuation of surface runoff. Remember we said our surface runoff takes place in two ways. It takes place in what we call sheet flow, and it also takes place in channel flow. You must be able to differentiate between the two concepts. And that's our groundwater. We said groundwater is water stored within the Earth's surface. Now what do we have there? We have what we call types of rivers. Types of rivers. Now we have different types of rivers. One type of river is what we call permanent river. A permanent river is a river that flows throughout the year. A permanent river is the river that flows throughout the year, which means it's going to have water throughout the year. The water volume might vary from 1 month to another, or from time to time, but it will be having water throughout the year. So when you're looking at the amount of water that flows in the river, we call it a river discharge. So which means now, with your permanent river, the river discharge can vary, but there's always going to be a river discharge for your permanent rivers. So during rainy seasons, the river will have more discharge, and then during dry seasons, the river will have lower discharge. Remember, the definition for river discharge is the volume of water as it passes a specific point at a specific time. Let's look at the next type of river. This is what we call periodic. Like when you speak of a period, we're referring to a certain time. So a periodic river refers to the river that flows only in the rainy season. Periodic rivers are the rivers that flow only during rainy seasons. One mistake that learners make is that periodic rivers flow only during summer. Periodic rivers do not flow during summer because rainy seasons vary from climatic region to climatic region. So we don't always have rains during summer in all areas. Some areas will receive winter rainfall, so their periodic rivers will flow during winter. Some areas have rain during summer, and their rivers will flow during summer. So periodic river is not a river that flows during summer. That is the common error that learners make. They say periodic rivers only flow during summer. They don't flow during summer. They flow during rainy seasons, because rainy seasons vary from one climatic area to another climatic area, or climatic region to another climatic region. Then we have another type of river that are called episodic. So episodic, from the word episode, it means there must be an episode of something. So episodic rivers will flow after a heavy rainstorm. So after this heavy rainstorm, after that episode of heavy rainstorm, then these rivers will flow. We call them episodic river. They flow only after a heavy rain. They don't flow during rainy season. So the rain must be heavy so that water can flow on the surface. Because if it only flows on the surface, if it flows gently, the rainfall is not that heavy. It's going to be more infiltration, and therefore the river will not flow. So these rivers require heavy rainstorm for them to flow. Those are your episodic river. And the last type of river that we're looking at here is what we call exotic river. Exotic river. So exotic rivers, what are exotic rivers? They are permanent rivers that originate in a rainy or wet area but later flows through a desert. So If we go back a few slides back, we can look at our river. Now, let's look at this river here. If this river here is flowing from this area of heavy rainfall, and then suppose here, this whole area over here is a desert. Suppose this whole area over here is a desert, but this desert is found between that heavy rainfall area and this a sea. The river has to flow past this area. At this point, this river will be called exotic river. At this point, if this area over here is a desert, if this area here is a desert or is a semi-desert or semi-arid area, at this point, the river is going to change its characteristics. It's now going to be called an exotic river as it passes this point. So it is actually a permanent river, meaning that it is flowing throughout the year, but at this point, this river changes how it is identified. It is called exotic rivers. So exotic river simply refers to a permanent river or as it flows past a semi-arid area or it flows past a desert. At that point, that river is identified differently. Like yourselves as learners, you are identified as a learner when you are in a classroom, but when you get to home, you are identified as a daughter or as a son. When you go to a friend, you are identified as a friend. So it is the very same person, which is yourself. So this river is a permanent river, but because now it is flowing over a dry area or a desert, it now changes how we identify it. We now call it an exotic river. Now look at permanent rivers. So here is an example of a permanent river. Why is this river flowing throughout the year? The reason why this river is flowing throughout the year is because of our water table. Now let's look at the water table. During dry season, the water table is still above the river. So this is a cross section. What you're looking at here, you're looking at the cross section of a valley. You're looking at the cross section of the valley. And then what are you looking here? You are looking at the water table. So like we said, the volume of water in this river will either increase or decrease. So during rainy season, a permanent river's volume of water or the river discharge in the permanent river is going to be higher. Why? Because the permanent river during rainy season has got two sources of water. Number one is got the source of water from precipitation, which is rainfall. It's got water from precipitation, and it has also water from the water table during rainy season. So that is why the volume of water will increase. But during dry season, there is no precipitation, so the volume of water in the river is going to decrease. The only source of water for that particular river will be the groundwater, and then this water will be flowing into that particular stream. I hope you know why the rivers will flow throughout the year. Now, the water table will intercept the riverbed throughout the year. So it has got the source of water throughout the year. So during the rainy season, it has got the source of water from the rainfall or from the precipitation plus the groundwater. But during dry season, it only has the source of water from groundwater. So this is how we identify. Permanent rivers on the map. They will have a solid blue line. They have a solid blue line. It is not dotted. It is not broken. So the line is solid and it is blue. So that is how permanent rivers are represented on the topographical map. Continue with the periodic river. Here is your periodic river. Now, look at the periodic river now. Let's look at the water table. the first water table is the water table during rainy season. So the water table during rainy season, it intercepts the riverbed. But during the dry season, the water table does not intercept the riverbed. So what does it mean now? It's only going to get precipitation. It's going to get water from precipitation and also from the groundwater, but only during rainy season. But once this rainy season is over, so there is no source of water from precipitation. Also, there is no source of water from the groundwater. So it cannot receive water from the water table or through the water table from the groundwater. It cannot receive water through the water table from the groundwater. So during rainy season, during dry season, this river will not flow, because the water table will only intercept the river bed during rainy season. That is why it will only flow during rainy season. And then let's look at how you are going to see the periodic river. So a periodic river will have broken lines. Periodic rivers will have broken lines because it does not flow throughout the year. It will have the broken lines. It does not flow throughout the year, and the river discharge will be higher during rainy season, and it will be absolutely not available during dry season. Then we have what we call episodic river. So what is an episodic river? We have already defined what an episodic river. So we can see now what happens with the episodic river. Why does this river only flow why does this river flow only after heavy rainfall? It will only flow after heavy rainfall. Why does it flow only after heavy rainfall? Because it does not have access to groundwater. So without heavy rain, there is no water for an episodic river. So there is no point in time when the water table intercepts the riverbed. There is no, remember when speaking of the riverbed, this is the bottom surface of the riverbed. This is the bottom surface of the river valley. We can call it that the riverbed. That is where the water is flowing on. So with your episodic river, at no point is the river, is the water table intercepting, or at no time is the river having access to groundwater. So where does it get its water from? Only from heavy rainfall. Without heavy rainfall, this river will not flow. Why? Because the water table never intercept the riverbed. So its sole source of water is heavy precipitation. So you can see there is no, and then how do you see that? You see that with those broken lines there, it's showing that it does not flow throughout the year, and it will also have little amount of water, because the only source of water there is flow for a short period of time and only after heavy rainfall. So it will also have a lesser discharge because some of the water will be infiltrated. Now this is let me quickly go back to this this water table here. Now when you're looking at this particular river, you can see the amount of water that you see in this river. Why do we have such a limited amount of water in this particular river? We have a limited amount of water in this river because, number one, no source of groundwater flowing into that particular river, and then because there is no source of water, no water table intercepting, so it will have very limited amount of water. The only source there will be your the only source there will be your heavy precipitation. Now let's look at your dendritic drainage pattern. Here is your dendritic drainage pattern. What is a dendritic drainage pattern? So let's look at the characteristics of dendritic drainage pattern. So there are 3 questions that you need to know when you're talking about drainage patterns. Number 1, you need to be able to identify. That's the first question. Identify. You need to be able to do that. And you need to give the characteristics. You need to give the characteristics. And then you need to give the reason why does it look like that. And then you also need to know the underlying rock. The underlying rock will be the place where that particular stream is found. That is the underlying rock. What are the characteristics of the surface where that river is flowing? Now, let's look at the dendritic pattern. We say it looks like the branches of a tree. Be careful, it does not look like a tree, because the different trees look different from each other, but the branches of a tree have similar characteristics. So you must not say it looks like a tree, because if you say it looks like a tree, you will be penalized for that. You have to state it properly. You say it looks like the branches of a tree, and the tributaries join the main stream at an acute angle, or you can simply say they join the main stream at an angle that is less than 90 degrees or smaller angles. So you can give those as your characteristics. Number 1, the question could be saying, identify the stream, the drainage pattern. You must know it is identify the drainage pattern. You say it's dendritic, and now give a reason. Why do you say it's a dendritic pattern? Because it looks like the branches of the tree. And then you can say the tributaries. So you can look, here are your tributaries that are joining the mainstream. So the tributaries are joining the mainstream at the acute angle. And now, where do we find these streams? What is the underlying rock? So that question can be said, where do we find this kind of streams? So that question is, describe the underlying rock. Describe the underlying rock. So that question is simply saying, where would you find this kind of streams? The area has the rocks here, uniform rocks of similar hardness. So here, the rocks have got similar resistance to erosion. There is no place where the rocks are eroding faster, and in other places the rocks are eroding slower. So you can see it can be granite, it can be gneiss, it can be volcanic rock. So when you look at these rocks, they will be the same igneous characteristics, or it can also be the same sedimentary rocks of same characteristics. It cannot be sedimentary rock followed by igneous rock, followed by metamorphic rock, because those rocks will have different characteristics. So it must be rocks of similar characteristics, or they can be folded. Here's another drainage pattern. Another drainage pattern is what we call a trellis pattern. It's called a trellis pattern. And now, you must be able to identify the trellis pattern. So when you're looking at the trellis pattern, you must be able to give its characteristics. You must be able to give its characteristics. What is the dominant characteristic that you can see? So you can see that the main streams are flowing parallel to each other. So the main streams are flowing parallel. You can see that main streams are flowing parallel to each other. That's another characteristic that you can see. And you can also see what the tributaries are joining the mainstream at 90 degrees. So the characteristics, tributaries joining the mainstream at 90 degrees. You can also see the tributaries are short. You can see we have short tributaries. You can see they are very short. And then where does it develop? It develops along a strike valley where smaller tributaries feed into the steep slope of the mountainside. So what are the underlying rock, or what is the underlying rock? Gentle sloping alternating layers of hard and soft. Alternating layers of hard and soft. Now let's look what you said here. Here we said with dendritic, the rocks must have similar resistance. Here the rocks must have similar resistance. So now look at how your dendritic will look like on a topographical map. This is a topographical map. So the question could be saying, identify the stream pattern. Identify the stream pattern at A, or identify the stream pattern at B, or identify the stream pattern at C. So the question could be identify the stream pattern. And then they say, describe the underlying rock. Describe the underlying rock. So all we know here is that this area here has got similar resistance. You can even see with the indication of contour lines. You can see with the indication of contour lines. The contour lines here, you can see they are very spread from each other. The contour lines here, you can see they are far from each other here. So those contour lines are indicating that. These contour lines here are indicating that this area has got similar resistance. Now, let's quickly compare this to the next one. Now, let's look what's happening here. So, with your trellis pattern, the rocks must have alternating soft rocks and hard rocks. So, where you have soft rock, you are going to get valleys. Where you have hard rocks, you will get you'll get your hard resistant. Where you have hard rocks, you're going to have your spares where you have hard rocks. Now let's look at here. What do we have here? You see, now we have contour lines that are bending towards the highest point, and then we have here contour lines bending towards the lowest point here. So you have your soft rock here, you have your hard rock here, you have your soft rock here, then you have your soft rock. So this is how your trellis pattern is going to develop. So what are the characteristics of the underlying rock here? It is soft rock and hard rock. So you can see you have stream here because there is soft rock. Here you have hard rock, then you have soft rock, then you have soft rock and hard. Here you have hard rock here. So your hard rock, the contour lines will always be bending towards a different direction towards compared to the softer rock. Your softer rock, the contour lines will be bending towards the highest point there, where the river is flowing from. So this is how you identify the pattern from the map. You identify it. So you'll see the different shapes of contour lines, other ones bending in the another direction. Where they are bending towards the highest point, then you are going to get the streams there. That is your valleys. Where they bend towards the lowest point, you are going to have your spares or your ridges there. So this will be identified. This is how you identify it on the sketch, on the diagrams. You will identify them from the sketch, from the diagrams, from your infographics. But this is how you will identify them from your topographical map. So you get them where you have alternating layers of hard and soft rock. There's a hard rock, there's a soft rock. Where you have hard rock, you get your spares. Where you have soft rock, you get your valleys. And then we said development, they develop along a strike valley where there are smaller tributaries which feed into a steeper slope of mountains. So here is your smaller tributaries. You see, there are your smaller tributaries that are flowing into this. So that is how they develop. And then characteristics, we said the main streams are parallel to each other. Why are they parallel? Because they are following soft rock, hard rock, soft rock, hard rock. Where is soft rock? We have a valley and a stream. Where you have hard rock, you have a spur and no stream. So that is how they develop. Now let's go to other type of streams there. Radial drainage pattern. So radial to radial is from the word radiate. So you have a high-lying area here. So the streams are flowing from here, they are going there, they are flowing from there, going there. The streams are radiating. So this is your radial pattern. The streams, water is falling on top of the surface here in Mahenge, and then it flows into the stream. So this is how you will identify it on the topographical map, but this is how it will be represented on different diagrams. Different diagrams will show it like this, but this is how you identify it. So if you are writing your examination and you see features and they say identify a stream pattern at point A or point what, you look, if you have those contour lines that are very close to each other there and you have the streams that are radiating there, you must know that is your radial pattern. Now let's look at the characteristics. They look like spokes of a wheel. So they look like a spokes of a wheel here in a diagram. So in a diagram they will look more like that, like a spokes of a wheel. But in the actual surface, remember this is not drawn on paper, so it will not be as clear as spokes of the bicycle when you are looking at it from the topographical map. So you can talk about that when you're looking at the diagram. And then what are the characteristics? You said it looks like the spokes of the wheel. And then what is the underlying rock? Rivers are flowing from away from a high central point like a butte or a mesa. So you can see this one over here, you can consider this like a mesa because you can see the contour lines here in the middle are a little bit open from each other. So this will be your type of radial pattern. Let's look at another one, a parallel. So when you're looking at the parallel pattern will look more like a dendritic pattern, but with the tributaries that are more parallel to each other than in a dendritic pattern. So this one will indicate that the slopes here, it occurs in regions with pronounced slopes with uniform rock that have got uniform resistance. So there is uniform resistance just like in the dendritic pattern, but here the slope will be more steeper, because when this slopes are steeper, then the water channels is not going to spread a lot. It's going to follow a single channel. So that is why now it becomes two parallel to each other. If it was a little bit gentler, then the tributaries will open wider. If it was a little bit gentler, and as it opens a little bit wider, it will look like a dendritic. But this one is a parallel pattern. You must be able to identify the parallel pattern. The rocks here, just like in dendritic pattern, the rocks here have got similar resistance. So how does it develop? Its development: rivers and streams are flowing roughly parallel lines over a sloping surface. So the area is more steeper as compared to the area in a dendritic pattern. And then what are the characteristics? The characteristics that the streams are swift and they are straight. The streams are a little bit swift and more straight. You can see here on the topographical map here, this will show you those kind of streams with very few tributaries as compared to the dendritic pattern. So there are few tributaries and all flow in the same direction. They all flow in the same direction. Let's look at another pattern. So this is your rectangular pattern. So your rectangular pattern will be, if you are in a classroom, it will look more like the bricks in your classroom. So if you look at the bricks in your classroom, they represent an exact rectangular pattern. So a rectangular pattern on a topographical map will look more like this. So what is happening here? You can see the area is very the color here is brown, is dominantly brown. So why is it dominantly brown here? Because there are too many contour lines here showing that the area here is very steep, So this is going to be developing where we have igneous rocks, but these igneous rocks have got cracks in them. So the underlying rock here, the underlying rock for rectangular pattern is jointed igneous rock, areas with hard rock that is well jointed. So you can also add that it is jointed igneous rocks. Jointed igneous rocks. That's where you find them. So where you have joints, the rocks will be weaker, and that is where the streams will flow. And then another characteristic that you must look at here, the tributaries join the mainstream at 90 degrees. So you can see the tributaries here joining 90 degrees, but remember, this is natural phenomenon. It's not going to be as 90 degrees as if somebody was measuring it or somebody drew it. So it will show those kind of characteristics of being very straight in terms of the angles. So this is you can see the mainstream have got 90 degrees bend along their course. You can see the mainstream having a 90 degrees bend, and then the tributaries also joining the mainstream at 90 degrees. So you can see this is a natural feature, but you can see it is trying to have those 90 degrees bend along its course. So why is that happening like that? So if you follow it like that, you can see the streams are a little bit parallel to each other as well, just like in your trellis pattern, streams being parallel to each other, and those 90 degrees bend that you can see. So the tributaries join the mainstream at 90 degrees. The mainstreams are also flowing parallel to each other, and the mainstream also have a 90 degrees bend. So we have two 90 degrees here. We have the tributaries joining the mainstream at 90 degrees. We also have mainstreams bending at 90 degrees. Tributaries join the mainstream at 90 degrees. Mainstream have got 90 degrees bend on themselves. So that is your rectangular pattern. So it is found where we have jointed igneous rock, or where we have rocks with joints or with cracks. So it can be joints, or you can also use the word cracks. Then development, the joints are usually less resistant to erosion. So the cracks, because we said it's jointed igneous rocks, so the joints are usually less resistant to erosion than the bulk rocks. So the bulk rocks will not weather easy, but through the cracks, that is where water is going to flow. So erosion will tend to open the joints, and streams eventually develop along the joints. Then what are we going to get there? We are going to have what we call your rectangular pattern. Then we have what we call a centripetal drainage pattern. Centripetal, as you can see it here, it is represented like that. So centripetal is an opposite of your radial pattern. Your centripetal is opposite to your radial pattern. Your radial pattern, the streams are flowing out or away from the high-lying area. But with your centripetal pattern, now you can see this is your high-lying area. You can see with the contour lines very brown, indicating that now water is flowing now from this high-lying area into this particular stream. Rivers are flowing from this high-lying area into these streams. So the water is flowing there. It is flowing there. It is flowing there. Water is flowing from the top, is flowing there. So this will be, this is what we call a centripetal pattern. It's opposite to radial pattern. The other name for a radial pattern is centrifugal, although it is not part of your examination guideline. It is not written like that in your examination guideline. So you must not use the words that are not in the examination guideline. When you study, you must always use your notes in relation or in conjunction with your examination guideline. Do not use the words that are outside the examination guideline, because you might be penalized for that, because that is not how you are guided to do your study. So the streams are flowing towards a central depression. So this is a central depression. It's a low-lying area. It's a lake. So the streams are flowing towards the lake here. So this is your centripetal pattern. Now, how does it develop? The fluvial network converge towards a central depression. So the fluvial, so which means the water network, it flows towards a lower lying area. So that is how your centrifugal pattern is going to form. Where do we find these streams? We find them where there is a dam or a lake. So you can see here what we have there. You have a lake, because you cannot be saying that is a dam because you don't see the dam wall there. So this will be a natural phenomenon there. It is actually it's called a pond. The name of this lake is called Den Hole Pond. So where do we find this? We find them where there is a dam or a lake. So you have a dam there, you have a lake there, you have a pond there. So water is flowing from this high point and is flowing towards that particular low-lying area. Now here is another pattern that looks more or less like that looks more or less like this one. But this one, you can see, where do you find it? Centripetal pattern. You find it in a higher lying area, where streams are flowing from a higher lying area into a lower lying area, like into a dam or into a lake or into a pond. Now let's look at what we call here a deranged pattern. So the name says it all, deranged. So the deranged pattern doesn't have a specific shape that we can give. It doesn't have the specific shape. It's asymmetrical. It's unlike any other thing. It's undefined. It can take any form. So you have streams that flowing into this lake, streams flowing out of this lake into that lake. So stream flow. So it is what we call a deranged pattern. So it is found mostly in areas that have experienced glaciation, which is the snow that was flowing there and resulted in the development of those particular streams, or it's in the swampy area. So that is your deranged pattern. Where does it develop? It develops in hills, valleys, and depressions. Dictate the flow path. The depressions will dictate the flow path. So these depressions, these areas that are lower, are going to determine that water must flow down there, resulting in a patchy and an unpredictable network. So the network here is patchy and unpredictable. So the streams are flowing into this lake, they're flowing out of this lake. So it's got different ways into that lake, out of that lake. So you can see another thing that we see here. You can see here you have swamps here. You have marshes and swamps here. So those are the characteristics of your deranged pattern when you identify it from the topographical map. It is very important that you are able to identify these streams on the topographical map, because you are not always going to be asked questions based on them. You are not always going to be asked questions based on the diagram. You have the questions, your 12 marks application questions in your map work, where you must be able to identify the streams on the topographical map. So what are the characteristics here? It has got an irregular, broken drainage system. The drainage pattern there is irregular. It doesn't have a definite pattern, and it is broken. And there is no coherent pattern to the rivers and lakes. So the pattern is not coherent. So the streams will flowing in, flowing out. So it is deranged. It's like somebody who has who's got amnesia is forgotten everything, so it's a little bit deranged there. Development, we said that it heals valley and depressions which are dictating that, and unpredictable network. Okay, where do we find this? Areas where there has been much geological disruptions. Those disruptions can be caused by either your glaciation, where we have flowing snow there, or flowing ice. Glacier, remember, glacier simply refer to a moving ice. It's called that. So it could be that particular area. Rivers have not had time to adapt to the underlying rock. So the underlying rock has no factor. The underlying rock here, that the type of rock that is found here has not much of the influence into whatever it has, because you say here rivers have not had time to adapt to the underlying rock structure and follow the irregularities of glacial deposition. So the underlying rock does not play a lot of a role in that particular stream development. Now at this point I will pause for 2 minutes and ask teacher Zondi to come and continue with drainage density and the map work. I thank you.
Good day, grade 12s. Okay, I will take you through the lesson. We are now going to look at drainage density. And then with drainage density, what you need to note is that this would be, it can come as a question where you have to define it. So it is imperative that you are able to define what drainage density is. Drainage density, it is the relationship between the total length. So we're looking at the relationship between the total length of the streams and the size of the drainage basin. So my colleague has explained to you the concept of a drainage basin. So when we look at the drainage basin and then we look at all the streams, the total length of all the streams that we can find within a drainage basin in relation to the size of that drainage basin, we then get what we refer to as drainage density. So the drainage density can either be high or low. So when we look at this hydrograph here that is illustrating to us that if we have a high drainage density, so it would mean that when we go to the drainage basin, for example, this whole of the drainage basin, we're looking at the whole cubic meters of this whole drainage density, and then we calculate the total length of all the streams that we can find here and we can identify here. So the total length of all the streams here divided by the size of the drainage basin would give us what we refer to as the drainage density. So here, as an illustration, is that we've got quite a few or quite a number of the streams that we can identify in this drainage basin. So the total length of all these drainage basins would then indicate that over a surface area, so if this would be the surface area that we are looking at, the total length of all the streams would assume this pattern of the hydrograph, so which says that there is high drainage density within this drainage basin. But then when we look at the comparison of an area now that has got a low drainage density, so we look at the total length of all these streams that we can identify within this drainage basin. So if you are looking at the size of the drainage basin, we can equally say that these two drainage basins, they are of the same cubic meters. So we've got the same size of the drainage basin. However, the length of the streams that we can identify in this drainage basin, it's less. So that makes the whole drainage basin to have a low drainage density, because the total length of all these streams that we find within this drainage basin, it's far less than the one that we can identify here. So if we look at the representation of the low drainage density in this graph, the hydrograph, which is the graph that is showing the total length of all the streams within a drainage basin. So we can see that there is less of the streams, but the area is the same. So when we look at area from here to there, it is the same size of a drainage basin. However, the total length of the streams there within this drainage basin, it is far less, and there's few of these streams that we can identify. So it makes this drainage density to be a low drainage density area. Okay, so what are the factors that influence the drainage density? So for an area of the same drainage basin, for us to be able to determine if it's a high or a low drainage density, there are factors that we look at. So these factors are precipitation, evaporation, soil moisture, vegetation, slope or gradient, and porosity, as well as permeability. So how do we differentiate, or how then do we look at each and every one of these factors to be the factors that determine the drainage density? So let's say, for an example, we've got high precipitation. So there is a lengthened period of time where we experience high rainfall percentages. So because the surface area over which the rain falls would, if the surface area reaches its saturation, like we can compare to the previous week where we were, is it a week or two, where we were experiencing high percentages of rainfall. So then the soil would be saturated, or the length of time that we experienced the rainfall, it will then have an influence on the drainage density, on the number of streams that we can find, or the volume of water that we can find on the streams would be higher, because the saturation would say that there will be more streams that would be flowing on the surface there. So high precipitation has impact in terms of having high drainage density. But then if maybe, for example, we experience less rainfall, so therefore it means if it rains, then we are not going to have more of water that will form part of the surface runoff. Therefore, the drainage density there would be lower. So the higher the precipitation, the higher the drainage density. And then the lower the percentages of precipitation, the lower the drainage density. Right, and then the other factor that we look at is evaporation. So when we look at the drainage basin that has got high levels of evaporation, so if there is more evaporation that would take place, so it means that we are going to have less of the streams that we're going to have flowing within a drainage basin, because this water would have evaporated in the form of a water vapor. So the higher the evaporation, the lower the drainage density. But then if we have less evaporation, then it means we are going to have more water that we can that can form part of the surface runoff. Okay. Then the soil moisture. So I have mentioned that in a period where maybe we are experiencing high precipitation, then it says that continuous rainfall would result in soils being more saturated, meaning that there is more of the water content already that is part of the soil there, and therefore the soils that are moist would have higher drainage density, because it would mean that there would be more of the surface water that we can identify than the soil that is dry. And then it can only be different if we're talking the soil that is baked, like the hard rock, hard surface soil. So if the soil is hard, it would mean that the water will not be easily passing through, but it can therefore result in the higher drainage density. So it depends on the type of soil, and then you should also be able to draw the difference that on soft soil where the water it easily gets saturated, then we are going to experience high drainage density. And then on soil that if there is less of the moisture in the soil, then if it rains, then water will just be passing through, and it would result in less of the streams that we can identify there. Right, then we look at the other factor that we can also do a comparison of. So areas that are densely vegetated. Areas that are densely vegetated, it would mean that if it rains, water would be passing through, and then it will be absorbed by the vegetation cover. Meaning that the higher the vegetation, the lower the drainage density, because vegetation would hold on to the water. But areas that are sparsely vegetated, so there's less vegetation, then those areas would have more of the water that will be forming part of the surface runoff, and there will be high drainage density. Then in the comparison of the slope, we are either looking at the slope that is gentle or the slope that is steep. So areas that have got a steeper gradient, there's more of the water that is flowing on the surface. So therefore, the density there would be higher. But in areas where the slope is gentle, then more of the water will not be just freely flowing, but it will infiltrate the ground surface, meaning that there is less of surface water, and it would mean that there is where there is less, where the slope is steep, there will be more of the surface runoff, and then the density there would be high. And then where the surface area is gentle, there will be less of the water on the surface, and the drainage density there would be low. Right, porosity, we're looking at the surface areas that allows water to pass through. So soils that are porous would allow more water to pass through, therefore there would be less drainage density there. However, the permeability, we're also looking at soils or rocks that are permeable, then it would mean that more water will be passing through, and then there will be less drainage density. However, if the surface is more permeable, then it means that water would be infiltrating the ground surface, and there will be low drainage density. So all these are dependent on the rainfall patterns and the surfaces that the water is passing through, whether there is more water that is infiltrated into the ground, or do we have more of the water that remains on the surface, and there will be more streams. So that's what brings in the difference between the high and the low drainage density. So these are all the factors that influence the drainage density, right? So linked to the drainage density, then we now know that when we have more streams that we can identify on the surface, then we must be able to calculate the stream order. So if we have a drainage basin that is indicated in this map extract, for an example, so with the stream orders, we identify all the source streams, all these streams that are the source streams. They are identified as stream order number 1. So as you can see from this map extract, all the source streams, or where the stream, the river starts to flow, they all are indicating stream order number 1. So this is the calculation of the geometric system, where now we calculate the stream orders within a drainage basin. So I have indicated that all the source streams, they would be stream order number 1. Then what happens is, when we now calculate the stream order, we look at any point of confluence between stream order number 1 and another stream order number 2, it changes the order. So here we've got this one, and we've got this stream order number 1. So there is a point in which these streams, they meet, the point of confluence. So that changes the stream order to say that the order of the stream now has changed. It's now stream order number 2. So when we identify the order of streams here, we say that this point is now at stream order number 2 because there's more water now that has been added to this particular stream. So when you look at all these where there's 2, we can see that, okay, there's a stream order 1, and then okay, let me leave this one for a while. Let's start here. So we can identify stream order number 1 and then stream order number 1 there. So there's a point of confluence here. So the order of the streams, it changes and it becomes stream order number 2. So meaning this whole stream, as it flows further down, now it's stream order 2. So even when it meets with this one, hence I said, let me hold on to that. So even if this 2 and this 1 meet here, the order of the stream, it doesn't change. So it remains 2. So a 2 plus 1 does not change the order, but a 1 plus 1, it changes the order. So here the order remains 2. Same with this one, stream order 1 plus a stream order 2, it will equal to this. So we don't use the mathematical addition here. We're using the geometric system of calculating the stream orders. So a 1 and a 1 is equals to 2. However, here, a 2 plus a 1, it's not equals to 3 as it would be correct mathematically, but with the stream order, there is no change of the order because this stream is not the same as that one. So the order remains the same. So we've got all the stream order 2, it comes, and now look at what happens. So we said this stream that is coming from this, is it north of northwest direction. So when it meets with this particular one at this point, the order changes now. So what will the order be? The order will be 3. So a 2 and a 2, where they meet here, then it changes the order to be 3. So how do we calculate it? Is that stream orders that are of the same order, when they meet, the order changes. But if there is a point of confluence where stream orders that are not of the same order, when they meet, the order doesn't change. So here we've got a 2 and a 2. It changed the order. So further, the stream now, it's on stream order number 3. But this 3, it will come across the other stream order number 1, so it will not change. It will still continue as a 3 here. And then coming to this side, we've got a 2. There's a point of confluence there. It will remain a 2 further down here. And then again, we've got this 1 plus 1, which gave us a 2 here. So now we've got this 2 that is coming from the north of, from a northerly direction. When it meets with this stream that is coming from a northeasterly direction, it's a 2 plus 2. We can see the order has changed there. And then this, the point where we see here there is a meeting point, it doesn't change the order because it's a 3 plus this one. So this stream, it comes long as it is, but it's still a low order stream. It will remain a 3 here. So I said here we already have another 3. Look at the point here. There is a 3 plus a 3. So this 3 plus 3, it changes the order, meaning that further down, this stream will be at stream order number 4. So you must be able to be patient and calculate all the streams so that you can get the correct answer should you be asked to calculate the stream orders. It is a possible exam question, and it may come as in a form of a topographic map, as you can see here, or it will come either in your question 2 of your paper 1, and then you must be able to calculate the stream order. So I said we are going to end up having stream order number 4, because here we still have 4 plus it's a 4 plus 1, this one here, and then it remains that. So this is just the system of calculating stream orders that are of the same. The order changes, it's a 2, and then we've got a 2 and a 2, the order changes to be 3. But if the order number 3 meets with a stream of order number 1, the order doesn't change. Same with this one, a 3 plus 2 stream order, it doesn't change the order. However, when a stream order number 3 meets with a stream order number 3, the order will change, it will be a 4. So continuously. So in our example here, we only have a 4 plus 1, because the last point of confluence here, it's this 4 plus this 1. So we still remain with a 4. And then if it's a 4 plus 2, the order still remains. And then 4 plus 3, rather not a 4 plus 3, a 4 plus a 4 would change the order to be stream order number 5 there. Right, so what are the factors that, what are the things that we need to look at when we calculate the stream orders, or what relationship do we need to understand in interpreting the stream orders? So as I've indicated, you can see your set of stream order number 1s that you can identify right at the source, and then all these, they have changed the order. Then we have a 2 here, and then this 2, it's another 2, the order has changed. Now we have got a 3. So here we've got this 2 plus this 2, the order has changed. Now we've got another 3. So all these 3 plus 2, it doesn't change. A 3 plus 3, so that's where we see the change of order there. There's a 3 plus 3 here. Now the order has changed. We've got we've got a 4. But this 4, it doesn't change further, because it meets with a stream order number 1, and it meets again with stream order number 2. So at the end, what we have is stream order number 4 as the highest order there. So what do you have to show understanding of? The relationship between the order and the factors that influences it. So the higher the order, the higher the density. So you can see that there's too many streams in this whole drainage basin that we are looking at there. So the higher the order, which is higher order number 4 there, it's because of the higher the density. So the more the streams that we have, they would result in the change of the order. So the stream order will end up being higher there. And then the other relationship that you need to know, the lower the order, the greater the number of segments. So if the order remains low, so it means we would be having multiples of the lower order streams there that are not changing the order. So the segments of the first orders, if there's too many of them and they don't change the next, I mean they don't change the order to the next one, then the order will remain lower then. Then the other thing, the lower the order. So if maybe we have got order number 2, for an example. So the lower the order, the shorter the length of streams. So if maybe we were just only looking at the drainage basin that is part of there. So you can see that this drainage basin, it would have shorter length of streams. That's why the order will remain at 2. But if you look at why 4 is the highest order here, you can see this stream, it's coming from far. It starts from here, and all these are the sources. So the higher the order, the longer the streams then. So the lower the order, the steeper the gradient. That's another thing. So where all these stream orders of order number 1, where we can identify them it is where the river starts to flow, and then the gradient is steeper then. Right. Then the other thing, the lower the order, the greater the total length of the segments. So if we remain with the stream order that is lower, it's because we've got more of, or we've got the greater length of the total streams that we can identify, but they are not changing the order. They remain in the lower order segment. All right. So it needs practice. Whenever you are using a map, you just have to find an extract that you can calculate the stream orders, and then you will know how to use that geometric system. Right, we are now going to look at some of the mapwork concepts that we are reminding you of, as most of you are busy with your mapwork task, or maybe you just need to relook at why maybe you didn't do well into your mapwork task if you already wrote it. Intervisibility. So this, it's also a concept that we have to show understanding of in the mapwork section. It refers to whether one point on a map is visible. So are you able to see one point from another? So one point on the map, is it visible from another? So can you see there's point 1 and then there's point 2. So between point 1 and point 2, we are looking at the fact that is this point visible or is it not visible? Can you see this other point from the other? So with our example here, we've got, is the dam at B intervisible from the, I would rather have this changed because we're not looking at the A being here, but our A is here, which is not the cultivated lands, rather our A is on the orchards and vineyards. So we're looking at point B, there's point B. So if you are here at point B, which is the dam that we can identify here, is the dam at B intervisible from the orchards and vineyards here at A? Or even if A was here, let's say maybe we can also move the A and put it where the cultivated lands are. So the question would still be correct to say, is B intervisible, or is the dam at B intervisible to A, which is the cultivated lands? The answer is no, because there is a build-up area. So we can see this gray scaling that we can identify here. It's a build-up area which is standing in between the 2 points. So when you are here, you cannot be able to see the cultivated lands that are at A here, or even if we are using the orchards and vineyards here, when you are at B, you wouldn't be able to see this. Why? Because of this build-up area. Remember, some of the buildings here, we're looking at it on a map as it is represented on a map, but there are tall buildings and all the height levels that we can think of. So this is not intervisible. And then the other example is point B intervisible from point C. So there we are at point B, which is the dam that we can identify there. And then we are looking at point C, which is this part. So between point B and point C, there is no higher ground, or there is no object that can prevent you from seeing one from another. So when you are at B, you are able to see what is at point C. So we say that B is intervisible to point C. So there's only the road that we can identify there. There's the road, the other road that we can identify there. And then the dam, there's a road and the dam between them. There's two features which are all low-lying. So all these features that are ahead of each other here between B and C, they are on the lower lying ground surface. So you can be able to see from there. Right, so we are now looking at the vertical exaggeration. So we need to have an understanding that vertical exaggeration is calculated either from a cross-section. So from a cross-section, you would have your cross-section that will either be representing a hill, and we calculate the vertical exaggeration based on the scale that is used there. So why do we calculate vertical exaggeration? To make features clear. So if we have a cross-section that has been drawn, if we differentiate maybe between a cross-section that is showing a feature that is like this and a cross-section that is just showing something like this, between these two features, this and that, we cannot be able to determine as to what feature is it, depending on just looking at how the cross-section is drawn. However, when we look at the vertical scale that was used to calculate, to draw the cross-section, that's where we can be able to clearly identify the feature. So we use the vertical exaggeration calculation so that we can make the features clear. It refers to the amount by which the vertical scale of a cross-section is made bigger compared to the map. So in reality, you may find that the feature looks like this, but when you draw it on a cross-section, it might not be a steep or it might not be having a clear defined shape like that. So the calculation of the vertical exaggeration help us to have a clear understanding of how the feature looks like in reality compared to the map, because remember, in the map it is put down in the in relation to the scale of the map. All right. So both the vertical scale and the horizontal scale, when we calculate the vertical exaggeration, they must all be in a form of a ratio. So if you have a cross-section would be showing the vertical scale of 1 centimeter equals to 20. So 1 centimeter equals to 20, like for an example, this one. So when you look at the vertical scale of a cross-section here, on the cross-section, it will be either indicating that 1 centimeter is equals to 20 meters. So meaning when this cross-section is drawn, for every 1 centimeter that is indicated here, it represents what? 20 meters. So it would not be possible for us to be able to put the whole feature how it looks like in reality if we don't use the scale. So the scale helps us to put that feature, if it's a mountain or a hill, it helps us to put it on a map, and we use the vertical scale there. So the vertical scale for a cross-section would be 1 centimeter on the map represents 20 meters. Therefore, this needs to be converted to a ratio. Remember, it would be given on a cross-section to say this is the scale that was used to draw a cross-section. So if we have a scale that is 1 centimeter represents 20 meters, this centimeters and meters needs to be converted. So your scale must have the similar units. So for us to convert the 20 meters to centimeters, because with 1 centimeter, but we've got here 20 meters. So what do? We convert the meters to centimeters. So how many centimeters are there in a meter? There are 100 centimeters. So when we use that King Henry died, miserable disease called measles. So we know this would be your kilometer, your hectometer, your decimeter. This would be your meter. So we put a 1 here, and then what are we converting it to? We're converting it to centimeters. So we say this. So this will give us a 100 centimeters. So in a meter, we've got 100 centimeters. So what do? We take the 20 meters that we have, and then we multiply it by what? By 100, so that we can have both the units in a ratio scale, both in centimeters. So that gives us 2000 centimeters. Right, so our vertical scale will therefore be, so that 1 centimeter equals to 20 meters will now be 2000 centimeters. So our vertical scale will therefore be 1:2000. Right, so we've already converted. Let's see how then we calculate. So we know our vertical scale is 1:2000. And if we are using a topographic map, so it means our horizontal scale would be what? Our horizontal scale will be 1:50,000. So here we've got 1:50,000 as our horizontal scale. And then here we've got 1:2000. So remember the other important thing when we calculate, you must do correct substitution. So when we correctly substitute this into a fraction, we're going to say 1/2000 divided by 1/50,000. So the cross multiplication of this, because you must divide the bottom by the top, you say 1/2000 times 50,000 over 1 there. So all these zeros, they cancel each other. We cancel all these zeros. 3 zeros are cancelled there. So we end up having 50 divided by 2. So this would give us this answer, which is 25 times. So always take note of the unit that you must use there. So 50 divided by 2, it gives us 25 times. So it means when we look at the cross section that we have drawn using that scale, it is exaggerated 25 times in reality. Okay. Then if maybe you are using the orthophoto map and the vertical scale there is 1:5 meters. So we're going to say this 5 times 100. Remember, we are converting the meters to centimeters. So this will give us, it will be equals to 500. So our vertical scale will be 1:500. And then remember, it is from the orthophoto map. And then our horizontal scale is 1:10,000. So you substitute the scales according to the fraction. So 1/500 divided by 1/10,000. So the same thing applies here. You divide the bottom by the top, and then you do your cross multiplication. So zeros cancel 0 here. So we've got a 0 that will cancel here. So what are we left with? We're going to be left with 100 over 5. And then to correct this, the answer would be 20 times. So the answer will be that if you were to to calculate the vertical exaggeration from a orthophoto map, that cross section, it would have been exaggerated 20 times, depending on what is the vertical scale that you are given. Right, boys and girls, we have come to the end of our lesson. Thank you for tuning in.